Welcome to the Cosmic Pie Podcast, Episode 15, Series number 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota. Now, we do have a chat feature that is running, so if you'd like to send us any comments or questions that you may have, please feel free to use that. Robert, do you want to start with the disclaimer?
The disclaimer?
We might have a few things to disclaim today.
Yes, we might. We know what's coming. Anyway, the opinions and all that expressed are those of myself and Wayne, not the University of North Dakota, the College of Arts and Science, or the Department of Physics and Astrophysics. So, we're it. We're the ones on the hook.
Now, at the beginning, we always like to mention, if we remember to do so, is that if you like our podcast, please remember to give us a thumbs up, not a thumbs down. Remember the old ancient Rome gladiator era. Thumbs down is not good as far as I know. So a thumbs up is what we would like.
I guess, depends on your point of view, but,
Now, and we also upload our podcast the next day on Spotify. So if you'd rather listen to us on that media, you can feel free to do that. Robert.
Yes.
How is your week going?
My week is, it's only Tuesday, but my week is pretty stressful and ongoing. So.
A lot of things on your mind, old buddy.
Oh, yes.
Oh, well.
Oh, yes.
Hopefully this podcast will brighten your day, and the rest of the week will be just fine.
Will be just peachy.
Now, if you're a big fan of human exploration of space, of course, you should be riding on Cloud 9. No pun intended there. And what's the reason for that, Robert?
Well, because Artemis 2 has been a successful mission. They launched successfully. They went around the moon, or they did a translunar
Free return?
Injection.
Yeah, translunar injection.
They went around the moon. They did their course adjustment to come back. They entered the atmosphere okay, and they splashed down and were recovered just fine. So,
yeah, big success story for sure.
one.
Now, we can start things off by showing you one of the images that the astronauts took on board Artemis when they were on the other side of the moon relative to us, and it caught my attention being a professional astronomer, and you'll appreciate it once I show you the image. And this is the image. This is an image taken of the central region of the Milky Way. And not only that, if you look in the very bottom right of the image itself, you see this sort of fuzzy object with like a bar-shaped pattern to it, or a feature, a straight-line feature. That's actually the Large Magellanic Cloud. So that's one of many sort of low-mass dwarf galaxies, as we call them in astronomy, that are in orbit around the Milky Way itself. But in the center of the image, that is the central region of the Milky Way. Now, Robert, looking at this image,
Right.
and comparing it to a time when I was actually down in Chile on top of the Andes Mountains at the Rubin Observatory, looking up at the sky at the heart of the Milky Way. So looking in this area. And with your eyes, you don't need a telescope, you don't need binoculars or a camera to record it. You can see, of course, the Milky Way, which we see at night in a dark location, but you can also see the large and the small Magellanic Clouds. And they're fairly nearby, as you see from this image.
Right.
But one of the things that I noticed is when you're there in person and you're looking at the center of the Milky Way with your two eyes, so you got this stereographic sort of view, if you like, is that it gives you this sort of three-dimensional projection effect that is something you cannot replicate in an image like this.
Right.
In fact, there's one dust line, you kind of see a hint of it there in the image, that when you look at it with your eyes alone, it literally looks like it's in front of the center of the Milky Way. It looks like it's projected outwards towards you. It's an amazing sort of view and impression. And that's why a lot of the sort of the views that we got on the Artemis mission of the far side of the moon, and NASA, mentioned the fact that, this is the first time you can see this feature with human eyes, like, for example, features that are near either the north or south pole of the moon. The Apollo astronauts were orbiting so close to the moon, like roughly 60 miles above its surface, that you couldn't see the polar regions of the moon from that location. They were below your horizon.
Right.
But when you're further away from the moon, like in this case with the Artemis mission, you could see that whole hemisphere, if you like, of the moon itself.
Yeah. Well, you mentioned something there that a lot of people do miss, and that is with the Earth or any other spherical object, even if you're where you can see the whole thing as a globe, as a sphere, you still have a horizon. You've got to keep pulling back before you finally see the whole thing. So, yeah, a lot of people miss that. That, yeah, you may be able to see the full circle of it, but you still have a horizon, and the further you pull away, the more of it, the more you can see.
Now, when with your eyes, if you're looking at some of these features, you're getting that 3D stereo vision. That's the thing here that you can't capture on normal photographs. Of course, we can take a photograph from slightly different positions
and get a baseline.
different colors, and you can get some stereo relief that way, of course. And people have done that in geography, for example, many years now. And so that's nothing new. But to see this features like this with your eyes, then it really provides that extra information, that depth perception that you wouldn't get otherwise.
Right.
And you get that with looking at the Milky Way. So it would be nice, for example, if one of the astronauts, hint, hint, if anyone out there knows them, that would have one of them invited here to the University of North Dakota and would come here and give a presentation of their mission. Hopefully they'll be making the rounds. Hopefully one of them will come here. And you can actually ask them, when you look at the Milky Way, do you see that three-dimensional effect like you can see when you're on the surface of the Earth looking up? And why I mentioned it was from Chile is because when you're in the southern hemisphere, the center of the Milky Way at times is directly above you. So you get that very, very good view then, a full view, if you like, of the Milky Way. You can't do that from the northern hemisphere where we're located because the Milky Way, the center region, is up at the middle of the night, let's say at midnight, only in July, but it's right near the southern horizon.
Right.
So it's really low in the sky, and so you cannot get the full effect, if you like, compared to if you're way down south when it's directly overhead. There is a big difference, and I mean a big difference.
And it's all because when the northern hemisphere is tilted towards the sun, it's actually tilted away from, at least from the point of view of the northern hemisphere, away from the center of the Milky Way. So, an unfortunate thing, but
yeah, and you're just looking through so much of the air,
the murk,
when it's really low to the horizon. So that's really problematic to look at.
Yeah,
and for somebody who's been looking at the sky ever since I can remember, so it's not like I just started to pay attention to what I can see in terms of astronomy. It's a huge difference. It's almost astronomical, should I say that?
Well, I'm taking students out. I have a few students coming out to one of the observatories for the university. And the last one I had out there, I was like, well, we got a lot of high-level haze. And this person was a little confused. This one looks clear to me. And I was like, okay, what causes me to say it? And I pointed towards the east, towards Grand Forks. And they were like, okay, I'm still not seeing anything. I was like, see that glow on the eastern horizon? That's from the city, and it should be down at the horizon. And it's about 40 degrees up into the air. There's a haze. And after you learn a few of these things to look for and look at, you'll never view the night sky the same way,
Yeah, it's very interesting. So to get a good view, if you can, in the future, I'm sure more people will get into space.
Right.
In fact, the exotic type vacations you can get here on Earth, you can go down and visit Antarctica and those kind of things. Now, in the future, it'll be visiting the moon, for example.
Yep. I agree. I have no doubt that's coming. Will it be within our lifetime?
I doubt it.
I doubt it.
But it'll get to the point where first you can just orbit, like go in orbit around the moon. In fact, to play it even safer, build a large spacecraft that can hold, 10 people, 20 people, and have them go to the moon and do the free return where they just literally repeat the Artemis 2 mission, go behind and come back. There's a 10-day vacation.
Yep.
And who wouldn't want to do that if you can afford the cost? Probably a lot of people, a lot of multimillionaires that exist today would definitely do that. I mean, they pay for rides to go, 370,000 feet above the ground in the Blue Origin craft, right? You pay a lot of money for those flights. So I'm sure there'd be a lot, or you pay money to go underneath the ocean.
Mm-hmm.
You know, all these, like I said, these exotic type of locations that you can go to. I'm sure there's lots of people on the world today that would pay to go on a flight like that. I mean,
Right.
I love to do that myself. I just probably couldn't afford it. But if someone gave me a free ticket in the future to do that, it'd be,
Hint, hint, nudge, nudge, wink, wink.
yeah. But as you mentioned, it was a great success, and so
Yeah.
here's an image on the next slide showing you the splashdown. That's always been problematic. It's not just the splashdown. There's even the touchdown. If you think of coming back on a Russian spacecraft, they land on the ground. You can think of Blue Origins, where they bring people up, like I said, to a high altitude. They also land on the ground.
Right.
And historically, you know, the Mercury, the Gemini, and the Apollo missions all landed on water for a splashdown. The space shuttle, of course, was totally different. I just landed on the runway like a plane in that sense, but it's a big glider coming in initially at Mach 25 times the speed of sound. So you just have to do your motions to bleed off that energy to slow down to around 200 miles per hour when you hit the long runway.
Mm-hmm.
So it was a different design. But now we're back to where we need splashdown again, using that sort of technique. And of course, the Dragon capsule uses that as well. So it's nothing new in that sense. But the critical moments, you know, a lot of critical moments. One critical moment, well, there's actually two of them. Number one is there was talk about the heat shield being problematic. So the engineers were confident they had everything done there that would not risk the lives of the astronauts. So clearly that worked properly. And now they're going to put a different one for Artemis 3. So they redesigned the heat shield to get rid of all these sort of issues that they were plaguing them for a while. And the other critical moment, of course, is the parachutes. So you had to make sure that the parachute system was such that three of them unfolded eventually. They had the drogue chutes that eventually pull out the main chutes sort of thing. But it all has to work. Obviously, you don't want to hit the water at 200 miles an hour. It would not be good.
Would be less than ideal.
Be less than ideal.
Yeah.
So
It's one of those things. It's not the fall that will get you. It's the electromagnetic force at the end that does.
exactly.
You know,
Counterbalancing gravity.
you know, yeah. I mean, I've tried pointing that out to people, you know, that when you put your hand on the table, atoms are mostly empty space. So what stops your hand from just passing through the table? And
Yeah.
the answer is, of course, electrostatic repulsion between the electrons.
Yeah.
So in essence, gravity takes you, if you jumped off the top of a tall building, you know, a few seconds to accelerate you to the ground. But the ground, the electromagnetic force stops you in microseconds.
Yeah.
So
As people say, when you're falling, you don't feel gravity. And then the joke is, of course, just give it a few seconds, you will,
right.
when you hit. But
That's
the parachutes, you can see there's three of them, all three of them unfolded properly. And back in the Apollo missions, they had the same kind of design, three parachutes to slow them down to roughly somewhere around 19 miles an hour by the time they hit the ocean. And in one of the missions, I don't remember which one it was, one of them did not unfold properly. So they came down on the two. And that's sort of the redundancy, is that extra parachute. As long as you had two of them that opened properly, it was easily survivable, the impact.
Right.
So
It still probably wasn't pleasant, my guess.
you hit a little harder than what you're used to, but not hard enough to cause any health issues, obviously, if you want to think. Or rapid disassembly of the spacecraft is the famous
Unscheduled
words.
rapid disassembly, yeah.
Famous words from SpaceX, right?
Right.
Now, speaking about the moon, and people often, they wonder, why are we going to the moon? Like, we've already done this, haven't we? Yes, we did it in Apollo 8. So we've done the moon. Why are we going back there? Well, there's a couple reasons, and one is the reason why we went there to begin with, and that's political.
Right. Yes.
China, for example, is planning to send astronauts to the moon. And, of course, countries like the United States are worried that if China goes there and sets up a base, they will somehow claim huge vastes or areas of the moon to be part of Chinese territory. And we don't want that. At least politicians don't want that.
Right.
And so that's an issue. And so once again, the driving point here is politics.
Mm-hmm.
And as scientists, we want it to be the science. But this stuff takes a lot of money.
Always has.
Always has. And therefore, to justify the amount of money that you need to do the Artemis project, doing it on science alone doesn't always work.
Right.
So,
And I hear people talk about that, and it's like, no, science wasn't always done. Yeah, there were the individual people like Newton and so forth that did it on their own dime. But like Da Vinci, he was hired by the Doge of which one, Milan or Venice? And he was doing most of his work at government expense. It's like, this is how things have been done. So, yeah.
But you think of it, it's, why was the United States settled? Why go out west? Right? Let's say you're
Right.
established in the 13 colonies. Why do you want to spread westward? Don't you have enough land around you to keep you busy for a while? And what was the driving force there? It's financial, right?
It was financial. Yeah.
To make money.
Right. But it wasn't funded by anyway.
Yeah. But that's so I always view this as a natural progression in human history, right?
We want to press. We want to go where we
Yeah.
haven't been before.
And as time goes forward, one could always imagine, yes, we'll settle the moon, then we'll go on to other places like Mars and so on.
Right.
This is a natural type of thing that we'll do. It might take a while, might take 1,000 years, but we'll do it, assuming we don't eliminate each other. Right? This is going to be a natural outcome of our
Right.
development as a species. So, anyways,
Yeah.
but speaking about China, interesting study that was released earlier this month. So this is on April 10th, so just a few days back, where Chinese scientists have released a study which they've done with their unmanned lander plus rover system that landed on the moon just a couple of years back. And they landed, in this case, the Chang'e 4 mission landed on the far side of the moon. Notice I didn't say dark side. There is
Right.
no dark side to the moon, people. I like to stress that because this came up, this misconception, again and again and again with the Artemis mission. If the moon is a new phase, then the far side of the moon is fully enveloped in sunlight.
Right.
It is not dark. In fact, at that moment in time, the dark side of the moon is the one that's facing us, the Earth.
Right.
But that constantly changes as the moon moves in its orbit around the Earth. And then after a period of one orbit, it's gone through 1 day. And that day is approximately 28 days long. So if you're on the moon, and this will be obvious in the future when we have a base on the moon, when you're on the lunar base, let's say Moon Base Alpha, the days are 2 weeks long and the nights are 2 weeks long. And that will become a routine type of thing, of course, when we have people that are living permanently on the moon itself. So that'll be, in popular culture at that point. But for now, remember, the far side of the moon or the back side of the moon is not in perpetual darkness.
Right.
Now, what Chinese has done is they landed a rover and lander on the far side of the moon and to explore it for the first time. We've never done that. The Soviet Union or even Russia hasn't done that. China was first in that respect. But when you're on the far side of the moon itself acts like a natural shield to all the radio signals that emanate from our own planet.
Yep.
And one of the problems that we have when we want to look for other intelligent civilizations to maybe eavesdrop on their radio communication, the so-called SETI program, the Search for Extraterrestrial Intelligence, is we want to listen for signals that are inherently going to be extremely faint. And what we don't want, of course, is to pick up any stray signal from the Earth. We want to make sure we're in a nice, quiet environment so we can listen.
I mean,
Now,
I'll put it in perspective. Do you want to listen to your friend sitting in an office with nobody else in there, or do you want to listen to them, try to talk with them at a concert with the speakers blaring?
yeah,
Because right now we're doing it from the ground on Earth, and we're at a concert trying to talk to our friends while the band's playing. And yeah, it makes perfect sense to go to the far side of the moon and set up the radio network there.
and then we got the national facilities, radio telescopes here in the United States, the National Radio Astronomy Observatory, NRAO, for example, and you can't be within so many miles of using a cell phone because the cell phones can be picked up by the radio telescopes and swamp the very faint signal that they're trying to pick up from astronomical sources. Now, what better way is to have your radio telescope on the far side of the moon?
Right.
And therefore, like I said, the Earth acts like that natural shield. So it's a very quiet environment. And the Chinese made use of this environment at the time by listening for signals then coming from beyond the Earth with the lander that they had on the far side of the moon. In fact, if we go to the next slide here, you can actually see the location of the lander and also the rover. So on the right side in the yellow arrow, it's pointing to the lander that's on the moon, the Chang'e 4 lander, and the rover is with the sort of lime color arrow pointing to that's on the left side. Now right away, this is the far side of the moon. Now this is an optical image. Do you see that it's all in darkness, Robert?
No, it looks pretty bright to me.
Yeah, it's pretty bright.
Looks at least as bright as the, let's see what, I can't remember. Anyway, the rock that it's made out of. Basalt and I think andesite.
Yeah.
Something like that.
And so that just shows you this image was taken by the Lunar Reconnaissance Orbiter, a NASA spacecraft that's orbiting on the moon, taking high definition images. And when it passed overhead of the location where the lander and the rover was located, of course, they took images, and you can actually see. You can see the shadow easily of the lander, for example. So yeah, that proves, number one, that somebody landed there, because you can see the hardware. And number two, it also shows you indirectly that, yeah, the far side of the moon is not in perpetual darkness.
Right.
But you can use, therefore, the radio signals to try to see if there's anything in that detection, just listening from the radio antennas. If you can pick up any stray signal then coming from beyond the Earth. And how do you do that? Well, the next slide gives you a flow chart. I don't want you to read it in detail, but it kind of goes through all the different steps that are required to analyze things like the radio signals that you pick up in this case. And there is a lot of stuff going on here. Basically, you take noise, so turn on your radio and then tune it to a station that has no signal and listen to the noise. And at night, it makes it a little easier if you're using AM broadcasts. So listen to AM stations and tune your radio. And you can tune it to an area where you can barely hear a signal. You know there's something there broadcasting, but you can't make out anything. You can't get any useful information, but you can certainly tell there's something there. And we can use sophisticated algorithms to look at the data, the digitized data, and try to, if you like, extract out any useful signal. And that's what's being done. That's essentially what this flow chart is showing, is different, Fourier transforms and all of these kind of things, these mathematical algorithms that people can use to try to extract out some type of useful signal.
And this gets into why do we call these pictures that were taken, why don't we call them pictures that the Artemis 2 group took? Why do we call them images? And it's part of this, because even with visible light, there's this type of processing that is needed simply to pull the signal out of the noise. And yeah, there's stuff that has to go on. Otherwise, all you'll see is static.
So they didn't expect to hear anything, obviously, picked up any kind of transmission from some civilization beyond the Earth, because number one, the radio wasn't designed to be sensitive like that. The radio detector receivers that they have on board the lander. So it was just a test, just to show you that it can be done, and we need to send something up there that's dedicated to this sort of thing.
Right.
We need to send a real radio telescope and have it on the far side of the moon, and that it is a much quieter environment than on the near side, where you're going to pick up a lot of signals, stray signals from the Earth itself. So it proves the technology. The only thing I worry about this, Robert?
The only thing I worry about is that we'll start sending up enough satellites going around the moon.
Thank you. That's exactly what I'm saying.
Will render that whole thing ridiculously impossible, because there'll constantly be a satellite in the way.
Now, right now, in order for that lander and the rover to communicate with the Earth, China sent up a satellite that's at the L2 position. You remember where that is relative to the Earth and Moon?
L2, isn't that on the far side of the moon?
Yes.
Yeah.
And
L1 is between the Earth and the moon, right?
Yes, exactly. And so at that position, the spacecraft orbits around the L2 position. And think of it as an oval, and the very center of the oval is that L2 position, which is directly away from the far side in a line connecting the Earth and Moon and then into space.
Mm-hmm.
And so if you stayed in that position, you still can't communicate with the Earth, right? The Moon would be blocking the Earth. But the spacecraft doesn't stay at a fixed location because the L2 position is not a point in space, it's a region.
Right.
And the spacecraft itself actually does this sort of closed loop orbit with the L2 position at the center of the orbit that it makes. So there are times when the spacecraft peeks out from the other side of the Moon relative to the Earth and can have a direct line of communication.
And you do a data dump.
And at other times when you're on the other side, and when you're continually going around in this pattern, in this orbit, you can have your line of sight then with the Earth.
Mm-hmm.
It's like peeking around the corner.
And like I said, during those times you do your data dump, and the rest of the time you just store it in onboard memory.
And the problem in the future is going to be, as you alluded to, we could have some very expensive and fancy radio telescope, let's say constructed on the surface of the Moon on the far side, trying to detect these faint signals, and you're going to be able to detect the communication from satellites.
Mm-hmm.
And the Lunar Reconnaissance Orbiter, for example, that goes around the whole Moon. The Artemis went around the Moon. So there are times when it's obviously on the far side of the Moon, and if they're trying to, is there any kind of electronic noise coming from the spacecraft, you're going to potentially detect that with the radio telescope because it's so sensitive.
And if it's electronic, it's broadcasting in the radio wavelengths.
And
There's
that doesn't
no way
mean,
around that.
Yeah, and that doesn't mean it's radio per se. It could be electric pumps that's running.
Mm-hmm.
It could be any machinery, right?
Right.
Think of spark plug. How you can hear car ignitions if you're tuned to the AM dial.
I was about to say, I remember the first time I changed out the radio in my first vehicle, my truck, that I had to then go get an electric conditioner because when you crank the engine, you could hear through the radio this from the engine running, and you had to filter that out. So yeah.
Oh, same as effect if you if you're listening to the AM radio during a thunderstorm.
Right.
You can hear the crackle of the lightning, and that proves that the lightning discharge not only emits visible light, it also emits radio waves, radio
Absolutely.
photons, because that's how your radio's picking it up in your car.
Yep.
So all these things can be problematic. So we have to really watch what we're doing. And I can see, what humans are like. I'm sorry, but in the future, it's going to be, now the far side of the Moon is too noisy.
Right.
And we got to go somewhere else. We'll see how all that plays out. But anyways, that's ultimately the idea. But you got to worry about how we treat the environment around the Moon for sure. Robert, there's been a lot of talk. How many months now about comets?
Oh, yes.
And I want to sneak this in. So there is a new comet, in a sense, that's out there. It's Comet C 2025 R3 PANSTARRS. So PANSTARRS is a survey of the sky that has been it's been going on for many years now.
Right.
And they look for things that are moving, like asteroids and comets and things of that nature, transient type sources. Observations are done from Maui in the Hawaii.
Oh, is that where PANSTARRS is?
Yeah, so there was a military, I guess you'd call it like tracking other satellites. So they had their own telescope on top of the summit. And astronomers started putting other telescopes up there as well, because there's some in Mauna Kea, that's kind of the big one, but there's also some on top of one of the other islands.
Mm-hmm.
Anyways, so PANSTARRS, periodically you'll see discoveries made from that survey. People are checking the data all the time, looking for things changing, for example. And one of the things it discovered many comets in the past, and here's a new one. Now, this comet is not well placed for us. Yes.
We have a question.
Yes.
And it's, what's up with the frequent sightings of fireballs in the sky right now?
Nothing unusual.
Yeah.
We're getting close to different meteor showers that occur. But other than that, it's just, it's like a lightning strike. Here's the way I think about it, right? You have a lightning strike, and then it always seems like then you have several more, like in rapid succession, and then nothing for a while.
Right.
So what happens there. Some of that is coincidence. Some of that is one triggers the other one and it's ready to go again type of thing.
And sometimes it's just a matter of these things have always been happening, but it's only in, let's say, the past 20 years that we've had the Internet of Things going, that something that happens halfway around the world is, online in 5 minutes or less. So
yeah, and this, what it is. Everybody got a Ring camera.
And everybody's got a Ring camera.
Everybody and his brother got cameras that are running, and they're capturing all these incoming sites. I mean, you can go, there's sites like spaceweather.com, which lists all the fireballs and records the numbers. And if you look at the numbers, there's really no difference year after year after year. They average out to be about the same. But of course, with the Ring cameras, and everyone got a camera in their phone, and that's in their pocket, they're capturing a lot of this stuff a lot easier than what they used to in the past.
Right.
And you can imagine a world in which like all of the land is covered by houses. Let's imagine that.
Let's not.
Every square inch of the land mass has a house on it.
Yeah.
Then how many of these things are going to be going through the roofs of people's houses, right, every year?
Right.
You see?
Yeah. I mean, I remember seeing my first fireball when I was, elementary school aged, and standing around with my dad and grandfather and going, what is that? Because it was just this bright streak that just seemed to slowly go across the sky. So they've been happening.
Yeah, there's a good way to detect some of that stuff.
What's that?
You can actually take a magnet and run it through your eaves of your house, and you pick up micrometeoroids.
Oh, yes. I did know that because we talked about doing that when I was at Case Western, putting a big sheet of plastic across the roof, pinning the corners down, and then putting a hole in the middle and weighting it down so all the water that it caught went down into. And while a lot of what you catch is grit and sand, if you hold a magnet to it, you'll find that there's a lot of magnetic material. And then one of the professors there had to burst our bubble because he pointed out, guys, you're in Cleveland, there's a lot of pollution. So you're not just getting micrometeorites, you're getting a lot of pollution.
Yeah. Part of what people are noticing too is about, we have meteor showers several days before the peak and several days after. You get increase in shooting stars and stuff.
Yeah.
And so the one coming up in late April is the Lyrids, Lyrids.
So there is a meteor shower coming up.
Yeah, in fact, there are several of them throughout the year.
Mm-hmm.
It's like it seems like you're not out of the shower possibility.
Right.
Very long, like maybe for a couple of weeks, and then bang, you're kind of in the next one coming, right? So there are many. There are like 10 or 11 or 12 of these.
There's one if not two or three a month.
Yeah, and most of them are very weak.
Right, and that's the trick.
Yeah.
But even the weak ones can produce a fireball.
Yeah. So anyways, there's definitely more shooting stars in that sense because we're heading into late April into the next shower. The one I love, of course, is the Perseid one.
Those are usually a big one.
Yeah, and because number one, it's summertime here. Mm-hmm. So you can lay out all night long on a lawn chair and look up and not freeze to death.
Right.
If for ones in January, there's one in early January. Not a good time in North Dakota to be laying out on your lawn that's covered with 3 feet of snow.
Yeah, I definitely do not recommend that.
Yeah. I'll see how strong you are.
0 stars, do not recommend.
Yeah, exactly. No thumbs up on that one, right?
No.
Now, this particular comet, by the way, is visible just before sunrise. That's why it's not well placed here. And so you got to get out there fairly early, a little bit before probably 6 a.m. So people are saying around 90 minutes or so before sunrise. But it's going to be very low in the eastern sky, unfortunately. But it's worth a shot. So tomorrow morning, get out there just before it gets daylight and see if you can see it. A pair of binoculars would be the best to use to look for this. And it's in the constellation Pegasus, so that gives you kind of a rough idea of where to look for. And you can look that up online, of course, exactly from your location where you need to look at.
Cool.
Now, to give you that perspective, the next slide actually shows you then, relative to Pegasus, where the comet was located this morning. So I didn't plot it where it was or where it will be tomorrow morning, but where it was this morning. And it's not going to change that much. It'll change a little bit. It'll be further down and to the left a little bit, but not a significant amount. And if you watch this podcast a week from now, it's too late by then, right? So this
Right.
has to be something you have to capture
Well, it's
in the next day or two.
if it's lower in the east, that means it's inbound, right?
It's getting closer to the sun, right?
Right.
So that's making it worse and worse to be able to see it.
But in a
Unfortunately.
month or so, we should be seeing it going outbound in the
And of
western
course, you
sky.
know when it's going to be observed then. Where do you have to be to get a good view of it then?
Oh, right. Okay.
Yes. You know
In
where
the
do you have to be, right?
In the southern hemisphere.
Yes, that's where they all seem. Why do all comets seem to look best when you live in the south?
Yep.
Anyways, so that's that.
Oh, well.
Now, speaking about comets and asteroids and all these things, I thought I'd talk about an update of the Vera Rubin Observatory. So this is a telescope that was just recently constructed. It's about 8.4 meters in diameter. It's built and it's located down in Chile, not too far away from the Cerro Tololo Inter-American Observatory, which I have visited several times. And it's up in the Andes Mountains, so you get one of these really good views of the center of the Milky Way, as we alluded to near the beginning of the podcast. This telescope is kind of going through its commissioning phase now, and so they're trying to work out all the bugs. It's a really complicated type of system. It's not extremely easy to use, and you say, okay, the engineers had it for a night, now it's all yours, astronomers, go ahead and do what you want. It's not so simple. So hopefully soon they'll really start going on this telescope, but they're collecting data now. And one of the things, and by the way, the beauty of this telescope, it is designed in such a way that it can observe the whole sky that it can see from that location. Every 3 nights you can cover the sky, which is just huge. I mean, the field of view is very, very large on this telescope. And you sort of take an image, you move it a little bit, take another image, move it a little bit, take another image, and you do that image after image after image after image. And you can cover the whole sky then in 3 nights on average. And you just keep repeating that. It's a sort of nominal lifetime of 10 years, but if everything works good, I'm sure they'll go way beyond that. And you just keep observing the sky, you keep observing, you just keep observing. And some of the things you can do is you can pile up the images on top of each other so that you can see fainter. And the other thing you can do, and this is the beauty of it, you can see things that moved from one image to another. So if you go back to the same location, let's say a couple nights later, an image, and then you compare it to the image that you took tonight, you're looking for things that changed in location and position. And that is a great way to see things like
Asteroids and comets.
asteroids and comets. And speaking
Okay.
of that,
It's got to be close to us if we see it moving over the course of a night or 2 or 3.
exactly. And so here is a slide that gives you an idea of some of the preliminary information that they have gathered already with the telescope in the engineering commissioning phase. Already, we've discovered almost 13,000 new asteroids.
Wow.
That's amazing when you think about it.
Considering the, 600 and some odd thousand main belt asteroids we'd already knew about?
Yeah, and this
Yeah.
is just the first part, and this, like I said, this survey is going to go for 10 years and more. So you can imagine you multiply that, but at least by 10, and be able to see a lot more of these things. And being such a large aperture telescope, that allow you to see fainter objects.
Mm-hmm.
So that would include objects that are smaller than the typical asteroid that we normally would see in a smaller telescope. Thinking of asteroids that are between, let's say, Mars and Jupiter, which most of the asteroids are located, but also allow us to see asteroids that are much further away, including finding objects way beyond the planets out in the Kuiper belt.
Yeah. What I want to see if we can actually finally see something in the Oort cloud.
Yes, that would be amazing.
That would
and that's
be incredible.
that's thousands of astronomical units away, where
Right.
an astronomical unit is just the average distance between the Earth and the Sun. And if you see objects that are thousands of AUs out there, you're looking out in the extreme outskirts of our solar system.
So
yeah,
that's what I would like to see.
That's where you get comets that are on these sort of almost, unbounded orbits.
Million-year orbits.
Yeah, where they take such a long period of time to go around the orbit once. So in our lifetime, if we're lucky enough, we'll see one of them, but that's it. You'll never see them again. And so who knows what's out there, right, in terms of maybe there's another planet, Robert, out there.
I would be surprised if they did that.
People have been looking for this.
Yeah. It would tell me it's either a rocky or icy body, because if it's a gas giant, should still be radiating in infrared, which we would have spotted.
And that's the key there. It would radiate in infrared wavelengths, and we've used infrared telescopes to do surveys of the sky, and part of that data was sift through to look for any planets that might exist far in the outskirts of the solar system.
And we have another question. How can we see galaxies millions of light years away, but not the Oort cloud?
Right, and the difference there is just in brightness. These galaxies are so bright because they contain literally hundreds of billions of stars on average. And the combined light of hundreds of billions of stars well outshines comets, which are only visible in the optical of reflected sunlight.
And they're usually tiny.
Yeah, they're small, and plus the amount of light that reaches way out in the Oort cloud, because light falls off as 1 over the distance squared. By the time it reflects off of them and comes back, you have that 1 over r to the 4th power effect.
Right. I mean, I'll put it this way.
Extremely faint.
I'll put it this way. Set up a dime, then walk 3 miles away from it and shine a flashlight at it and see how well you can see it.
Yeah.
That's the difference. Whereas if you put a spotlight the same distance away, you can see it just fine.
Yeah.
That's the difference between an Oort cloud comet or ice ball and a galaxy.
Yeah, and the problem is, if the comet itself was like a laser, and the laser was shining directly towards us, then we could see it easily.
Easily.
But it's just, we can only see them in the optical because of reflected sunlight.
Right.
That's the problem. That's why they're so faint when they're so far away like that, like the outskirts of our solar system. Now, the interesting thing too is when we survey the sky in infrared, and for example, you can go online and look at all the data. It's free. It's deposited there for anyone to look through. From the WISE satellite, this was an infrared all-sky survey that NASA did with a space-based telescope just a couple of years back. People have looked through that data set looking at hints of a possible planet, and none were seen.
None were seen.
So that doesn't mean there's none out there. They're just based on what we have done so far, given our technology, given our survey strategy, we haven't detected any. So, and if they are out there, maybe they're really far away, therefore very hard to detect, or they're in a weird type of orbit that has a really high inclination.
Yeah. And again, Extra Bullet is basically trying to get at why we can see these galaxies. And you're right, the spotlight is 1,000 miles away compared to the dime being 3 miles. But it's that same issue. This is why we don't see galaxies with our eye. We have to get a 16-inch diameter eye to be able to see them. And it's all tied in together. It's all wrapped up. You've got to have a big enough eye. You've got to take a long exposure. I'm doing, like I said, observations with students right now. We're using 16-inch telescopes. And to see even nearby galaxies in a 16-inch telescope, we're taking 4 to 5 minute exposures. And that is just to see them. So, yeah, when you see these pictures, these nice, pretty pictures, you're probably talking, 20, 30 minute or longer exposures, even through a massive telescope. So this isn't a matter of, they can see this. Yeah, because they're doing a lot of things to make it possible. So, the Oort cloud isn't seen because, the same reason we had telescopes since the 1700s, and we didn't see Pluto until 1936, thereabouts, with, I think, a 100-inch telescope. I think it was the Mount Wilson.
No, it was Lowell Observatory.
It was Lowell, okay.
I think I forget the size. It was like 24-inch.
Right.
They took photographs, and they compared the photographic plates looking for something that moved.
Right. So with the Vera Rubin, we're talking 8.4 meters. We're talking, let's see, what would that be in feet? We're talking about 25, 26 feet across. So we got a huge eye. They're probably not taking that long an exposure, but they got a huge eye, and they're doing it night after night after night. And so this tiny little fleck of light from one of these comets will be seen. But, you know, that's why we haven't seen them before now. You
And
know?
just for perspective here, one could ask the Trivial Pursuit type of question: what is the most distant object that you can see with your eyes? Not allowed to use binoculars or telescopes or anything like that.
That's
And the answer
Andromeda.
is,
That's Andromeda, isn't
yeah,
it?
the Andromeda Galaxy. And you might say, well, why can I see that? And that galaxy, by the way, is 2.5 million light years away. So the light, if you go out tonight and look at the Andromeda Galaxy, the light enters your eye, left that object 2.5 million years ago. But it's you know, as far as we know today, it's slightly more massive than our own Milky Way. It could contain upwards to around 400 billion stars. So it's the combination of light from all those 400 billion stars and the fact that it's relatively close, considering the size of the universe, that allows us to see it with our own eyes.
And to be quite blunt, in extent, it's the size of the full moon. So, yeah, it's really putting it out there. So
For sure. Now, Extra Bola mentions about too bad we can't send a space telescope out to orbit Pluto, for example. And you know, one of the nice things about that would be
well, yeah. Then
the
we could get
difference from
really
here
good.
to Pluto is about 40 AU.
Mm-hmm.
So we're getting a little closer, but not really a lot.
Right.
It would help to survey the Kuiper belt more, for sure.
Mm-hmm.
But if the Oort cloud, thousands of AUs, going 40 AU closer is not that much of a difference, you
Right.
see? But the interesting thing about this is if you could make observations from the Pluto location, 40 AU away, and compare it to observations that we can make in space and orbit around the Earth, we have two positions on which we are observing things separated
by 39, at least 39
on
AU.
average, let's say 40 AU for sake of argument, because
Okay.
we're
Yeah.
about 39 and sometimes 41 away. So let's
Right.
take the average 40. And that will allow us, using trigonometry,
Yeah.
parallax, to get a very accurate measurement of the distances to stars in the Milky Way.
Yeah,
So that's the beauty there.
and yeah, space telescope out there. Yeah, okay, it takes 20 hours to get a signal back, but you know, yeah, there's all kinds of things. We're so far away from the murk and the glare of the sun that all of a sudden, you know, right now we can resolve stars in the Magellanic Clouds and in Andromeda
And in some other galaxies.
and in a few other close
nearby,
galaxies.
yeah.
But from out there, we'd probably be able to start
Yeah.
resolving stars from, you know, a little further out.
In fact,
Holy cow.
what I'd
Yeah.
love to have out there would be some radio telescopes
Mm-hmm.
that were hooked up with the Event Horizon telescope system so that we could resolve black hole shadows in the center of a lot of galaxies. Now we only use two. We've only seen two
Yeah.
because of that resolution issue.
Interferometry is a lot easier with radio telescopes.
Yeah.
So yeah,
That's
three
and that
radio
will happen in the
telescopes at
future.
Pluto. Holy cow.
That's going to happen in the future.
Yeah,
that will
the
definitely
resolution
happen.
and everything would just be chef's kiss.
And that's only a matter of money. We got the technology, right?
Yeah.
It's just a matter of money to do that.
A matter of resources.
Yeah, exactly. Now, the next view is the hamburger in space image.
Hamburger in space.
Yeah, it looks like a blue hamburger
Oh,
in the
okay.
image. This is a James Webb Space Telescope. We haven't really talked much about that
Mm-hmm.
space telescope. I thought I'd throw this in here. This is a beautiful image of a protoplanetary disk,
Yes,
a
yes,
solar
it is.
system that's forming. Now, this object is about 480 light years away, so it's relatively nearby. But the details that you can see in the disk is incredible when you look at it.
Yeah.
And it does
I mean, you can
look
see
like
the
a hamburger, right?
Yeah, you can see the inner disk, the outer dark disk. You know, yeah.
Anyways, this is making me hungry. Maybe we should move on. But this
Yeah.
is this. So we can actually resolve and see solar systems forming, and this is one that's edge on. Of course, we've seen several of them too that are face on,
Mm-hmm.
and it's very interesting to see how planets clear out their orbits of material. We've seen that in different situations.
And
But-
is that red object a background galaxy?
No, that's just gas in that area
Okay.
where it's forming. So,
Okay.
but it's the galaxy that you can see in the background is actually way over on the left and then way over on the right.
Okay.
You can see the spiral-like pattern associated with it. Yeah. So those are definitely galaxies and fire in the background. And then the other objects you see that look got a weird pattern around them, those are stars in our own Milky Way. Yeah. What's all this food talk? It must be close to supper time here.
Must be close to supper.
Time to speed up, Robert, so we can get here and get to supper.
Right?
Now, thinking about exploring different things in our solar system, this is an interesting study that's recently been published. One of the things we'd like to do, of course, is to land where, Robert? In our solar system. Place that's forbidden that we go there now, kind of toasty.
That'd be Venus.
That would be Venus. And let's jump to the next slide as we're talking here. Now, this is what the surface of Venus looks like, at least from one location. And this is observations that were done in the middle 1970s, long time ago. For a lot of people,
Hey.
A lot of people who are listening to this podcast may not have been born at this time.
Oh, all right.
But this is from the surface of Venus, taken by the Soviet Union spacecraft, Vernia 9 in this case, and they landed a couple of them, I think 3 altogether, if I'm not mistaken.
All 3 of them lasted around an hour, and only one of them, the camera actually worked.
Yeah,
So.
I mean, as you see there, the average temperature on the surface of Venus is a little toasty, 464 degrees Celsius.
It melts lead.
Yeah. And so if you have a device that landed there, like a lander, and even if you soft land somehow, and it's made up of electronic components, those components are going to melt eventually. Mm-hmm. Now, you might have them inside of a refrigerator-type air conditioner.
Sooner or later, you run out of power and coolant.
Sooner or later, yeah, things are going to end catastrophically for you. So what you really like to have is you like to be able to develop electronics so that they can survive this yellow hell, as Extrabulla refers to, and he's not wrong there, that's for sure.
Wrong.
I mean, not only as you have pressures about 80 times Earth pressure, there's the atmosphere contains sulfuric acid and so on. Not a good place to not a place to visit on your honeymoon, put it that way.
Nope.
So what they have developed, which is hopefully leads into potential future exploration of this planet in fine detail, are these memory devices, memorizers. So they're memory type of devices that can survive up to temperatures of 700 degrees Celsius.
Nice. And I could see a few practical purposes for that.
Oh, yeah, there's lots. But, of course, the one that immediately I thought about was, hey, couldn't we develop, a lander with this type of technology and be able to survive for not just an hour or so on Venus, but also for weeks or months?
Right, maybe.
Venus is relatively unexplored. I mean, we've had the Magellan spacecraft in orbit around Venus to use radar to get a sense of its topography. We've had a few landers, as we mentioned, from Russia. We had Pioneer Venus spacecraft that was there and sampled the atmosphere by launching probes into the atmosphere to see what the composition is like and so on. But it's relatively unexplored. And Venus is about the size of the Earth. In fact, it's a lot of times known as the twin Earth. Until you look at what the temperature and the atmospheric conditions are like.
And the lack of a magnetic field.
Yeah, and then it's completely opposite from the Earth at that point.
But we do have Extrabulla asking, why don't we use technology like on the Parker Solar Probe? And the answer is it almost certainly would take technology of that sort.
And don't forget the probe was set up such that, number one, it had a heat shield in front.
Right.
In this case, the heat shield has to be all around it.
Mm-hmm.
And number two, as you know, the difference between temperature and the density of the particle field that you're in. If you want to say more about that.
Well, basically, we say that the solar corona is at millions of degrees. But for an astronomer, temperature is just a proxy for the kinetic energy of the particles. So when we talk about the corona, you're talking about something that there's one proton in a foot square cube. So it's not very dense. But the particles in that 1 foot cube are moving so fast that it's like they were at 2 million degrees. So you've got to watch out with that description of temperature. If you're talking about a rarefied gas or plasma, we're usually just proxying for the amount of the average kinetic energy, Whereas if you're talking about like an atmosphere like Venus, you're talking a dense medium, and you're actually getting what most of us think of as temperature. So,
We should invite a scientist to talk about plans to explore Venus for the United States. And see
I mean, there's been plans for a long time.
Let's see what's up with that. That would be a good idea.
Yeah.
A planetary scientist in here. Now, if you were going to put a lander on Venus, Robert, where would you put it so it had the best chance of surviving, given present technology?
Honestly, I would probably actually not land. I would probably do something like a balloon or a...
No, you have to land, Robert.
Okay, if
Don't
we have
cheat.
to land...
You got to follow the rules of the game, old buddy.
Okay. Then I would probably burn some energy and put it into at one of the poles.
No.
No?
You know what you should do?
What's
Put
that?
it on top of one of the extinct volcanoes because you're extremely high up.
Fair.
The pressure is a lot less and the temperature is a lot lower.
Yeah.
Those are the places that you'd be able to survive the easiest of all the places on Venus.
I could see that.
That's where you'd want to go.
Yeah.
So that's prime real estate in the future. You want to talk about
Yeah.
the south pole of the moon and things like that where there's potentially ice under the soil. Go to one of these high peaks on the surface of Venus where the conditions are
A little more favorable.
a little better. Maybe by the development of technology like this, we'll be able to survive there. Okay, Robert, are you ready for it?
Yeah.
Let's do this.
Let's ready for this. Dun.
Now for the bad news, folks. So the President of the United States has submitted his proposal for the budget for 2027. And if you're a scientist, a major disaster.
You're crying.
For example, as you see there at the top, the National Science Foundation, 55% recommended cut. NASA, 23% recommended cut, 47% of which is out of the space science budget.
Right.
Department of Energy, the Office of Science, 15% cut. NIH, the National Institute of Health, 12% cut. NOAA, keep an eye on not only
Hurricanes.
earthly weather, but space weather.
Yeah.
27% cut. The CDC, 41% cut. The U.S. Geological Survey, 37% cut. The EPA, who needs environment, nice clean air and water, 52% cut. And even the U.S. Department of Agriculture, a 19% cut. Now, there's things okay. The budget is nearly $40 trillion in the whole, right? That's the amount of money soon that the United States will owe. Number one, how do we seriously attack the budget issue? You look, first of all, for things that swallow up the vast majority of the money. Now, part of this budget is $1.5 trillion for the Department of War. The rest of the money is really in Medicare, Medicaid, Social Security.
Yes.
And then everything else, including the things you see on this line here, makes up the rest of it, which is very small in number. Very small.
I've done the numbers. What you see on that slide is less than 3% of the budget. Less than 3%, folks.
Yeah.
You're not gaining anything cutting that out, and you're losing. I mean, people think that NASA and all these science programs are just wasting money because who cares what's going on in space? But in solving our problems of how we get information from light, there's no telling how many. Actually, there is a lot of telling how many marketable inventions have come out of that. So it's not just, we've learned about space. It's that we've learned about better sensors and detectors that are now in your phone as your camera. We've gotten all these, the Apollo missions, one of the things that came out of them was cordless tools. Because you can't exactly run an extension cord from Earth to the moon.
I thought it was Tang.
Yeah, well, then there's that. But, we are... People think we're doing a lot of good by cutting these programs because they're just waste, but we're actually cutting our throat.
If we don't have time to go into detail in every single one of them, so we maybe pick this up in another future podcast. But if we just concentrate on the NASA budget, none of the Artemis stuff is being cut. It's all in the space science.
Right.
And that amounts to, like I said, 47% cut. Overall NASA budget, you see there 23%. And the head of NASA, Jared Isaacman, the person who, of course, and he should do this, was celebrating the Artemis 2 mission. He was asked, of course, about these budget cuts. And most times, you think that whoever is the head of the agency, if you're getting a budget cut, even though you might vote for that party who's now in power, okay, that you'd say, this is not a good thing, these budget cuts, and especially being this high. I can see across the board if everyone took, a 5 or 10% cut as a way of symbolizing, hey, everybody's got to feel the pain in all of this.
Right.
But these kind of cuts are catastrophic. And unfortunately, NASA administrator, because, and I don't know if this is true or not, but he seems to come across as the person that cares more about the human part of NASA in terms of exploration of space rather than
actually getting
the space science part of things, the robots and the telescopes and stuff. He has announced he's happy with this budget. This is exactly what he'd expected and to come from the president. And this is he fully supports it. Now, of course, the NASA administrator is a political appointee, unfortunately. And we can argue whether or not that should be the case in the future. But, not to stand up at all for this dramatic cut in space science. And the thing is that someone might come along and say, well, get private industry to do this. Well, no. Private industry is not interested in sending a probe to explore the atmosphere of Uranus or Neptune. Private industry is interested in getting a transportation system that can put people and equipment in space to make a profit. Because that's what a business is there for, is to make a profit. If your business does not make a profit, you don't exist very long, do you?
Nope.
So there's no way to fill in this gap by going to private industry to say, hey, how would you like to help us build this probe to go investigate this? Look at the great science we'll get back. They won't support that. You know that. Right. That's why the government has to support that.
You're being, no offense, but actually, I'm not even going to say that. You're being disingenuous when you think that private industry is going to pick all this up. Private industry has never, ever in the history of humankind done pure science research, ever.
Now, last year, to be fair, Congress, after people got upset over the 2026 budget, Congress reinstalled, if you like, brought back the money that was cut, at least most of it. But in this case, we're going to get hammered again because, number one, we have some elections coming up, the midterms in November. So Congress is going to be busy with that. And so the chance of getting these proposed cuts reversed, in a sense, it's going to be very difficult this time around because of that. In fact, this money may not be brought back, if it is at all, and you never know until it happens, of course, until much later on in the fiscal year, not by October 1st, because of the elections in November. So there are a lot of people who are going to feel pain, and I mean pain as in you lose your job. And these are high-tech, high-educated type of jobs. And you know where people go when they lose their job in these type of fields?
In these fields, they go to other countries.
They go to other countries. Have fun bringing them back.
Right.
Who wants to go through this every year?
Or every 4 years.
It just doesn't make sense. It seems like we can do a much better job than this if people really, appreciate what the money is actually going to and what impact it has on our society as a whole.
And for people who say it doesn't matter, I will point out an anecdote about Michael Faraday, who was a rich, wealthy person. As his spare time, his hobby, if you will, he researched about electromagnetism. And at one of his society demonstrations of electricity and magnetism, afterwards, a lady of society came up to him and goes, Mr. Faraday, this electricity thing is all well and good, but of what practical use is it? And Faraday's answer was supposedly to look at her and go, Madam, of what practical use is an infant? Yeah. So we're talking about, you're just worried about getting your job cut. We're talking about basic science research, but electricity and magnetism were once just pure scientific research. You cannot tell where this stuff will lead. Yeah. You just can't do it.
Think of the invention of the laser.
Right.
What was that useful for? And now people use it to fix their eyesight, You know, and do all kinds of things, communication, you name it.
Even to scientists at one point, lasers were a curiosity. Okay, that's neat. Who cares? So, yeah.
You know, if you want to live in a country that leads, you got to spend money on R&D.
Yes.
You have to, and that includes supporting the basic sciences as well. And natural technology flows from that, which gives you the money to pay back what you invested, and many, many times more.
Right.
That's how it's worked historically. Why won't it be the same in the future?
And the answer is it will be. Anyway.
So we can talk about that on a different day.
Yeah.
But it's time to wind down this podcast, to close the shop, to go home and have supper, because I am now starving.
Or go out
after
to the
this
observatory.
Talk about hamburgers and everything else. But I just want to remind folks that next week, so it'll be April the 21st, on this podcast at 5 p.m., we have our very special guest, Dr. Andrew Knoll from the Harvard University, who is a paleontologist and author of several books, will be our guest. So please stay tuned for that. If you have any questions you'd like to ask him, make sure that you get on there on the chat and send us your questions while we're doing the podcast. So that would be a great thing. So join us live then at 5 p.m. Central Daylight Time then next Tuesday.
Yep.
Now, Robert, we always leave you with a quote at the end of our podcast.
All right. What we
I'll
got
try not
today?
to cover up the camera today like I did last podcast. All this new setup, see, I got to get used to this thing.
Right. Yeah.
Now, today's quote is by David Grinspoon, one of those planetary scientists involved in the exploration of Venus.
Okay.
It's one of those people you like to invite on the podcast, and I think I'm going to do that, see if we can get him on here if he's not too busy in the next couple of months or so to see what's up.
Okay.
So here's a quote from David Grinspoon about Venus. If you were on the surface of Venus, assuming you could see the sun, because it's so cloudy, obviously.
Right.
Which, would be hard because it's so cloudy there. But the sun would actually rise in the west and set in the east. And it would do so very, very slowly because the planet orbits incredibly slowly. Now, Venus orbits backwards compared to the Earth.
Rotates backwards.
Rotates
Yeah.
backwards compared to the Earth. In fact, as he mentioned, the sun rises in the west and sets in the east because of that backwards rotation. A day on Venus is 243 Earth days. So when the sun rises on Venus, by the time it sets, you have to wait about 117 Earth days. Crazy. And here's a crazier thing. You ready?
Huh?
The time it takes Venus to orbit the sun once, its year, that's what I was thinking when I was first saying it, is 225 Earth days.
Yep.
So Venus's year is shorter than its day. Think about that.
Yeah.
Now, if you like this podcast, one of the things you could do, of course, is come to the University of North Dakota, where we have lots of programs, both online and on campus. So you want to think about the STEM fields or even the arts or anything else that you might be interested in beyond the sort of K-12 experience that you had when you were younger. Please come here to the University of North Dakota. I'm sure you'll find something that piques your interest. And remember, be a lifelong learner. And with that, of course, we will end the podcast for today. Please remember to give us a thumbs up if you liked it. Subscribe if you haven't subscribed, and we'll see you next week. Thank you very much.
Bye, folks.